Good evening and welcome everybody. My name is Obi-Wan Pez and this is N Simplex Pachinko. We are going to be working on cracking the GRE math test tonight. This is the book from the Princeton Review, 2nd edition 2002. It was the one that I used for my GRE test back in 2005. And we are currently using the source of problems that are in it in order to look at all of the individual topics that are in each of the courses that are running all the way from pre-calculus all the way through topology. We have not actually, or I personally have not taken topology, but I am willing to put myself out there when we get toward that end of it and see if we can't do any work on some of the more advanced topics. Come on, Spotify. Welp. I'm going to just leave it running in the background and eventually it'll work, so probably. If it doesn't crash the tab. That's fine too. Hey, there it is. Alright, 20 seconds before it gives out. Right, so we want to reset. Oh, went longer than 20 seconds this time. Nice. Right. So we're going to look at proving derivative rules. We started with, hey Zach, how's it going? We're going to start with the kind of like easy functions that you just see kind of in the book, and maybe they've been laid out for you, and maybe they haven't. So it's good to check out what's going on with those things. And then we also... and a happy Wednesday to you too. Without a little more structure during the week, the days just kind of run together. Right, we want to check out which derivative rules we've already proven. That doesn't help. Oh. Oh. Wait, what? Ah, okay. So, as it turns out, tonight is actually night 17. Night 16 was last time. And, I think, right? It's 13th. Yeah. And I forgot to label, or I didn't label until after we started. So, hooray. Let's see, at the very end we talked about inverse function rule. Okay. So we did the three major rules from last time, and we proved them. Right, product, quotient, chain rule, and inverse. Right, so when we take the derivative with respect to x of f of g of x, then we are expecting to get f prime at g of x multiplied by g prime multiplied by g prime at x. Product, we said we want ddx of f times g of x, and this is going to get us f prime at x times g at x plus f at x times g prime at x. And the quotient rule, if anybody needs to see the workings out of how these all came to be, you can check out the last couple of streams. We did stuff on proving how each of these things works. Cool. All right, I just altered the name of the VOD, so that'll be a little clearer as to what's actually in it. So we do f prime at x times g at x minus f at x times g prime at x all over g at x bracket squared. And inverse function rule said that if we have derivative ddx of f inverse at x, this is going to be the same as 1 over f inverse. Now hang on. I've got it on the other screen anyway. It is a rather hot night in Yorkshire, and by hot I do mean that yes, it is in fact only 30-ish degrees outside Celsius, so like 85 or so, but like it's after dark and we're still just not getting our heat inside the house down, so it gets maybe not the best. This was f prime at f inverse at x. Okay. Okay, so we looked at these particular derivative rules from last time. We're going to be given these because, again, we proved them last time. So if we want, for instance, taking the derivative of, good evening and welcome everybody from, shoot, I don't see it. It's Rogan27 and the Virginia Tech Library Studios, where Rogan is one of the archivists, attempting to explain all the awesome stuff out there. So welcome on in, everybody. It's lovely to see you. My name is Obi-Wan Pez. I also go by the handle nSimplex Pachinko. It's this place. Hello, hello. I am originally from the Northeast, so New Hampshire specifically, and had been living in Maryland for about 15-ish years before my family decided that we were going to go live in Yorkshire for 3 years. So we are in Yorkshire, England. It is currently about 30 degrees Celsius, and probably about that in this room, which, you know, is a little warm for England, especially given the humidity level. But Nuggets, good evening. Loving some Yorkshire. You alright? Alright. So, lovely to see everybody. Thank you for the follows. And bonus points if anybody knows. Only 25C in your office. Yeah, I would be very happy to have 25C at the moment, especially in this room. Although, to be fair, in the winter, having about 22, 23C in this room is very nice. Okay. So, we are currently looking at cracking the GRE math tests. This is the math subject test some people may have to take before doing graduate school. This is the particular edition that myself and my spouse used in 2005, well, 0405. When we were taking our GREs before going into grad school. So, and before moving to Maryland. Oh, I thank you so much, Rogan. Thank you for bringing everybody over. And if anybody is looking to talk about other sorts of math or anything like that, typically the schedule here is that on Sunday, we have Satisfactory Sunday. So just a little bit of games, having some fun. We're currently working on getting oil and a automated tractor route. Mondays, we do math education talks, and we've been working out of Building Thinking Classrooms by Peter Liljedahl. I attempted to use this in my community college class with mixed results, but let's be honest, most of it's probably my fault. I only got to really do it once for real, and there are some hang-ups just because of my style, organization, etc. On Tuesdays, we just started a run of 9 sols. So we just did our first episode yesterday. We retreaded the first section of the game and now are like off in an area where I've never been before. I played probably 20 hours worth of the game before I decided that I was going to stream it. So we're in a completely different section of the game, so I've never been there before. Makes it fun. It is also a game about a Tai Chi cat, so always a little fun. On Wednesdays, as you see here, we're going to be working on like mathy type questions, and we're specifically working out of cracking the GRE just for the like organization and the source of getting a whole bunch of math problems. If anybody has any particular questions about anything, I will pretty much always stop and answer your questions about any sort of math topic. So feel free and ask questions if you have any. The live audience always takes precedence over whatever nonsense I've planned. So, and on Fridays, we've been playing Against the Storm, which is a city building roguelite, which is a little weird when you say it like that, but it's kind of a fun game. Not super well known, but it's like from 2013, so you may or may not have heard of it. It's pretty cool. And then Thursdays and Saturdays, generally speaking, I just relax or port stuff to YouTube or play some Elite Dangerous because, you know, just cuz. So again, thank you everybody for coming in. Thank you, Rogan, for bringing your community. And we will continue on. So we're going to prove the individual functions derivatives. This is Calculus 1 for anybody who may not be super familiar. And the idea here is that we've got these rules that we have derived from the main definition of derivative. So here we take the derivative of the function f of x, and what that really means is we're going to take the limit as some value h, which is a distance between a point and another point on the function, starts getting closer and closer to 0. So as these points come together to almost be on top of each other, we're saying what is the trend of these objects. So these points, as they get closer and closer together, define a more accurate secant line that will go through the curve and be close to... Well, that's interesting. That's also me. So my account must have gotten here finally from Rogan's. Interesting. So as these points get closer and closer together, it starts defining a tangent line, which is a line which only touches that curve exactly at one point, and in effect what that's doing for us is it's showing us what the slope of that curve is. Most of the time you can't think of slopes of curves because they themselves are non-linear. But when we start getting a tangent line to a particular curve, then we can find out what its slope is at that particular point. So this is as these 2 points are coming together, we look at what it's doing, how it's trending, and then say, like, because of this trend, this is going to be the slope. So here this is defined as taking the function that we're looking at a point defined by the x value, x plus h. So some x value plus a little distance, which we are allowing to go to 0. And we're saying we want the distance in the y direction, in the function direction, between these 2 points. Some particular point f of x, or x comma f of x, and some other point over here, x plus h, comma, f of x plus h. Normally we create a secant between them, but again, as we get closer and closer and closer to the other point, it starts forming a tangent line. We are just using the exact same slope equation that you may remember from Algebra 1, where this is going to be the difference between our y coordinates on top and the difference between the x coordinates on the bottom. This then also makes the denominator, since this is x plus h minus x, those x's are going to subtract out, become 0, and we're just left with h in the denominator. So now we've got the slope of the line connected by 2 points, which are now becoming closer and closer and closer together. This, as h goes to 0, shows us what the slope of the tangent line is to the curve. Okay, so that's our definition for derivatives. All right, and our notation for that is the Leibniz notation rather than the Newtonian notation, because Isaac Newton, as much of a boss as he was, wrote notation for himself, not for other people. Whereas Gottfried Wilhelm Leibniz was first and foremost a math teacher who did some research. And because he was a math teacher, he knew the importance of communicating the ideas. So he developed a notation that was much easier to read, and those are the sorts of things that we still use today. Leibniz also was accused of being a plagiarist by Sir Isaac Newton because he wrote up essentially the exact same thing that Newton did, but completely independently. Like he didn't read Newton's stuff. And Newton didn't like him very much. Partially because he was also German, which wasn't really a thing at the time, but that's not the point. History. Alright, so we're going to take this stuff and then prove individual functions' derivatives. So, our f of x in each of these cases is going to be a particular function, and then we're going to take the limit as h goes to 0 of f of x plus h minus f of x all over h, and then we're going to put it in shorthand. All work can be done on the side. Okay, so if f of x is equal to k is a constant. So what's going to happen in this is that we're going to have something that looks like this, right? Y equals k. It is a flat line. It has no deviation in the vertical direction at all, and as such, its value is not dependent upon x in any way, shape, or form, which means we're going to get the limit as h goes to 0 of k minus k all over h, which is the limit as h goes to 0 of 0 over h. So as we put any number in the denominator, f prime is just going to be 0. Right? It has to be a finite number that is slightly larger or potentially slightly smaller than 0. We want to know what's going on as h gets really close to 0. So no matter what we put in there, we're going to get 0 over a number, which makes us have 0 as its derivative. Now, one might argue, well, 0 over 0 doesn't count, and I would say, yes, you're 100% correct. 0 over 0, if h were actually equal to 0, does not work at all. It is an indeterminate value, 0 over 0. As such, we can't use it. So you never are actually able to plug in 0 to somewhere that's going to get us an indeterminate form. If you plug in h equals 0 and it gets us a determinate form, which tells us about where it's going, then awesome. We'll use it. But until that happens, if it's indeterminate, can't use it. So we just say, what's the trend? Now this also makes sense because this is going to be the slope of the original function. So y equals k is a flat line. It has 0 slope. X to the k, we already did this. So we did this last time. The idea here is that we get a binomial x plus h raised to the k. K is just a constant. Minus x to the k all over h. What this is going to do is it's going to look at the binomial distribution of x plus h and this actually relates to my channel name. So the n simplex pachinko has to do with the things, the structure of the things that are inside this parenthetical, and the power k. So the idea is that the number of terms you have added on the inside form what's called an n simplex. If you were to look at them a little bit differently. So if we look at x plus h parentheses to the k, right, k equals 0 gets us 1. K equals 1 gets us x plus h. K equals 2 gets us x squared plus 2xh plus h. Nope, not to the third. Squared. K equals 3 gets us x cubed plus 3xh plus 3, x squared h plus 3xh squared plus h cubed. Okay, this pattern is going to keep continuing. And what's really important in this particular pattern is actually not the terms themselves so much as the coefficients that are in front. So looking at this particular pattern that exists, what we see is that in order to get the next numbers in the next row, we don't actually have to go through the process of actually multiplying this thing out every single time. What we see is that there is a pattern to these particular numbers. This is the number of ways in which you could, for instance, start a marble at the top and then choose which way to go. So if this goes left, then right, there are 3 ways for marbles to get to this particular location. One is to go left, right, left, or right, left. So there are 3 different paths to get to that particular location. And that's true of every other place on the entire, this is Pascal's triangle, better or lesser known as Liu Hui's triangle, because Liu Hui did this in, I don't know, I forget exactly, it was like 1500 years ago. Liu Hui did it as just sort of an exercise in number theory, in just having some fun with math. He played around and he made this entire structure. Now, how did he do it? Because he didn't know about like marbles dropping through a thing. He didn't really think about it in terms of binomial because they didn't have the same sort of algebra. No, he just did it as a mathematical game. If you start at the top and you imagine a field of zeros everywhere and a single 1, and then from there it's going to go down to either the left or the right. Academy of Useless Ideas. Good evening. Welcome, everybody. We are discussing my channel name and binomial theorem as it is used in calculus to help us prove the derivative of x to the k. Right, so the idea here is Liu Hui would have looked at this as just numbers that were in like a hex grid. And so if you look at it as a giant hex grid with our hexagons sort of pointing that way, you could think of these as either hexagons like that-ish or like diamonds or what have you. The points are headed down. Then the lines along the bottom will either go to the left or right. Right, one way or the other. And then if we say every single square or every single hexagon will contain the number that is equal to the sum of the two numbers above it, then we end up with, again, we start with a 1, and then out here is just all a bunch of zeros. So this one is going to be a 0 plus a 1, which gets us 1. This one is also going to be a 1 plus a 0, which is going to be a 1. And then we continue on through the whole thing. This is going to be 1 plus 1, which gets us 2. 2 plus 1, which gets us 3. 1 plus another 0 from out here gets us 1 again. Right? Liu Hui worked on this as a number theory problem. He just basically built a whole hex grid and said, these are the rules, let's go. It wasn't until the 11th century anyway. Wasn't until the 11th century that Muhammad Musa ibn... Nope. I always mix up. Muhammad ibn Musa al-Khwarizmi came up with the entire idea of algebra, or al-jabr, that a few of the other mathematicians in his time yeah, that one. Al-Kharaji. Okay. Al-Kharaji came around and said, hey, this thing that we've been playing with for, centuries at this point has an exact application through this binomial theorem that we've been working on for the past, 10 years. Isn't that really cool? So a number of the Islamic mathematicians, hey famished, in and around the area started playing with how to find binomial expansions by playing with this particular, well, we know it as the Pascal triangle. That's a travesty. Don't worry about it. But Liu Hui's triangle. So dating back to, again, old China. And Liu Hui was from GRE. Yeah, about 260s CE. So, yeah, 1800 years ago from now, give or take. So, what we're looking at here is the binomial expansion of all these things. Now, what's really cool, and the reason that my channel name is the way it is that if you decide to instead make this a trinomial expansion or a quadrinomial expansion, whatever it might actually be called, etc., right? Keep extending this. Tetranomial, I suppose, considering tri is Greek. Yeah. Right? So, in this particular case, we get a trinomial expansion. And in this case, we get a tetranomial. And, like, this gets really hard. Famish, would you like me to call you Slim? I guess I have seen it in a few chats in the last few days, and I just didn't quite make the connection. Oh, Academy of... There we go. Right, so Academy of Useless Ideas. Sorry, you talked with each other and I lost track of everything. Oy. Woo! So, no, presumably famished would not like to be called Slim. Woo! Alright, so the trinomial expansion actually gives us the same 1 on top when k is equal to 0. But when k is equal to 1, now we have a decision to make. Are we going in direction A or B or C? So now we have to have a 1A plus 1B plus 1C. This has a shape. We could decide to write it linearly like this, or we can fit it in a triangle. So this is now going to be a 1, and then on the next row, this is 3 1s affixed. Like this. From up top, the 1 could have dropped to this one, or dropped to this one in the back, or dropped to this one in the front. When k is equal to 2, we could have that we dropped into 2 a's. Sorry, we could have dropped into a and then a again, or in those directions. Or we could have dropped into the b direction twice, or we could have dropped in the c direction twice. Or we now have 3 different possibilities to get us into the a direction and the b direction in some order. So we could have gone either AB or BA to get to the same place. So now we got 2AB plus, again, oopsie, square. Again, same deal with the B and C directions. We could have dropped in through B then C, or C then B. And so that gets us to BC. Or we could have dropped C and A, or A and C, which gets us to AC. This becomes a little bit harder to start working with just algebraically. If you're like writing all this stuff out, this gets really hard to follow really quickly. However, if you do what I just said, and you say, okay, well, our picture here shows us that we could have dropped in the A direction again, or we could have dropped in the B direction, that'll get us to this place, or we dropped in the B direction first, then the A direction. Now we've got 2 here. Right? Or we could have dropped in the C direction, or sorry, in the B direction twice. So now we're here. Right? And then we also, you know what? I should not do these in the same color. Give me a sec. Let's go like this. Right? Green for the ones that are on the same level. We could have dropped in the back there for the C direction both times, and we get a 1. We could have dropped in the A then C or C then A, and so that drops us this way. So that gets us a 2 here. And again, same deal on the other side. So each level can drop like a marble or what have you from one number to any one of 3 numbers underneath it. And in each of these cases, right, we have the diagram here to show exactly where this is happening. So working with a diagram might be a little bit easier. It also gets rather unwieldy when we start doing stuff in higher dimensions, because, for instance, our a plus b plus c plus d to the k is a 4-dimensional figure. So, like, how do you do 4 dimensions? The easiest way that I figured out to do it is to work in 3 dimensions, but now it's like multiple pictures. And again, what we're really concerned with is what are the coefficients for all these things. So this becomes a 1, 2, 1, 2, 1, 2 in some order. This also becomes really hard because now, like, again, how are you going to order these things? You could choose how to order it, but it's going to get hard pretty quick. All right. So for the trinomial expansion, we get this thing. I was doing some research with some students at my school, in parallel, not together. Some of the students that my dean was working with had decided to look at just the standard Pascal triangle over here and say, you know, what are some patterns that are going to occur in this particular triangle? So, for instance, one of them said, what are the multipliers if you move across the row? And naturally, as we multiply through across the row, all the odd-numbered rows are going to have 1s in the middle, for 3 times 1 is equal to 3. And then also the 1 times 3 equals 3, and 3 times 1/3 is equal to 1. So now we've got like a reciprocal symmetric pattern that we're working with. Another group said, if we concentrate on this 2, for example, what are the 6 that are connected to it? And do they have any sort of interesting patterns? And there was some cool stuff. There was some cool stuff that they like pulled out of it, but I don't know that it. Sorry, I don't know that it's worth more than novelty, I guess. But it was a good research experience for them, because they were like, you know, let's ask a question and let's address it and let's find all the possible ways that we can disprove ourselves and just all sorts of cool stuff. Another group said, if you take this and you notice that the front face is just the Pascal triangle again, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, etc. Then if you were to remove that face, you'd be left with this 1 here, and then this 2 and this 2 behind it. right? The next face, you get 1, 2, 2, 3, 6, 3, 4, 12, 12, 4 going across, which, like, that's really cool. It's also a constant multiple of the original, where those numbers are increasing by 1, the multiplier is increasing by 1 every time. And then if you slice off another face, it turns out that the multiplier is increasing not linearly, but I believe quadratically. I have to look at the research again, but that was a really cool thing that they had figured out. I, on the other hand, was going level by level and looking at the sum of all the numbers on this level in this particular, like, slice, in this dimension. So we say, okay, everything that has a k coordinate of 0, 1, 2, etc., we're going to add up all the coefficients of that particular k value, and that's going to get us a pattern. That's not anything that's new, but nonetheless. I then said, if we look at the sums of the entire slice, then what is the pattern between the individual sums? And I found out that it is multiplicatively convergent. So it's like we're multiplying by a number that is getting closer and closer and closer to a certain number. And I was like, that's cool. I want to take that one. In the standard, right, binomial, this one's super easy, right? The sums are all going to be 2 to the k. Right, that's super easy. You could just look across. True. And again, you can verify that for any other row that you want. Whereas in the trinomial expansion, that's not the case anymore. So now we've got 1, 3, and 1, 2, 1, 2, 1, 2 is 6 plus 3, 9. Right, so the sums going to be 1, 3, 9. Now you might think, oh, look, it's multiplying by 3. That's not actually the case. 2, 4, 6, 7, 8, 9. Yeah. Just checking. At least I really don't think that's the case. Let me just double check. 1, 3, 3, 1, 3, 3, 1, 3, 3, and 6 in the middle. Yeah. So we get 6, 6, 6, and 6 is 24, 25, 26, 27. No, okay. It is. Never mind. That, for some reason, that felt wrong. I don't know why. 3 to the k. Okay, well... I must have done something wrong, or there's something that I'm missing, something that I'm forgetting. Oh, you know what it is? Okay, it's not this. It's, I started playing with the number of rows that are being calculated. So I said we want to do a multi-row sum. So the first 2 rows here don't change. If we were to do, for instance, a Fibonacci sequence, and in this case, again, n is equal to 2, so we get a binomial. Then what we're going to get is that you add the 2 previous rows to get the next thing. So the edges are going to have 2's. And the middle one is going to sum up all numbers within this diamond. So that ends up being a 3. So 1, 1, 1, 2, 3, 2. And then again, to get the next row here, we're going to do the same thing. So we want to add the 2 numbers that contribute to that particular location. That's just going to be a 3 on both ends. And then the numbers in the middle are going to be, hang on, let's not confuse this. To get this one here, we're going to take the 2 numbers above it, and then the 2 numbers contributing to those as well. Wait. Yes. Right, the 2 rows above that are contributing to that particular thing. Yeah. Should be a diamond, but... Alright, whatever. So anyway, this is going to be 5, 6, 7. So 3, 7, 7, 3. It's going to be that row. Now find the sums. So we got 1, 2, which again, right, we're multiplying by 2. That's not a surprise. That's just the original Pascal triangle. The next one, though, is 3 plus 2 plus 2 is going to be 7. That is multiplied by 3.5. And then the next one is 14 and 6 is 20. This is now 2 point something that we're multiplying by, right? So the factor right, the factor is going to be multiplied by 2, multiplied by 3.5, and multiplied by 20 over 7. I can't be bothered to do that one just off the top of my head, but 2.8-ish. And then as we go further and further and further down, right, this number, the factor, converges. So it does something that looks, roughly speaking, like this. All right, now that's a terrible representation because it's not... it's not actually continuous, right? This is a discrete set of values, but the dots are slowing down around this particular number, whatever it might be. So, like, what number is it? And then, given that the original one was just multiplying by 2, the factor was 2 for the Pascal triangle. This Fibonacci simplex on n equals 2 gets us a particular value, which is different. What I then termed Fibonacci simplex, one that adds the previous 3 rows to get this particular one, has a different value, which again, as we start doing this with larger and larger and larger like sums of k, we end up with different and also converging factors for that particular behavior. And I believe that it was the Fibonacci simplex that I said, okay, what we're doing is we're basically going like this and then summing up all numbers that are above this particular location, and all numbers above this particular location then contribute to this number, right, in a diagonal. So every number that ever contributed to all numbers above it that it's connected to are all being summed. Now this is a ridiculous thing. Nobody would ever do it, except, you know, a bored math teacher. And we actually did find that there is a particular value that all of this converge to. the Fibonacci simplex n equals 2 had a factor value that converged to, I believe it was 1 plus the square root of 3. So I worked out what the value was by just expanding rows upon rows upon rows inside of a spreadsheet. Yes, I know, don't at me. And kept the factor of each thing just over on the side. And as we went further and further down, I kept the factor of, the sum of the whole row and then the factor that we get from one line to the next. And eventually we just went down until the computer ran out of decimal places. Right? Once it ran out of ability to worry about precision. Because again, it was Microsoft Excel. Don't hit me. I could then track it to, 13, 15, 20 decimal places or something like that. I tried it out to 100 and it yelled at me. I think the issue was that it was rounding numbers that were further down. So it was like, some number times 10 to the 100th power. It wasn't keeping all 100 numbers. So I figured that out pretty quick and said, okay, we need it out to n number of decimal places, and then we know it's only accurate out to, and I did the calculation, it's only accurate out to like 12, 13 decimal places, something like that. And then I looked at this number and I'm like, I know what that is. I don't know why I know what that is, but I know what that is. It was like, what, 3.7? No. 2.7. Yeah, 2.732050876. And I'm like, I know those decimal places. I don't know where from, but I know those decimal places. And eventually I was like, wait. And I took my trig stuff that I've been working on, and I said, what's the square root of 3 over 2? It's, 0.866. What's that multiplied by 2? Oh, look, it's 1.7320508. And I was like, that's it. We got it. So, that is the extremely long version of this story. Sorry. Point being that we could then work with this familiarity with doing binomial distributions and say that our binomial distribution ends up with the sum of terms that have let's see, I going from 1 to n of this times x to the I 0. That's not even x, right? No, that's right. Okay. X to the I and h to the times h to the n minus I. Yeah. Or switch them around, I guess is the more typical way to do it, but nonetheless. X to the n minus I times h to the I. And the coefficient out front is going to be n choose I. Right. Suppose that needs a k in there somewhere. And choose k. No. K choose I. Alright, there we go. So x plus h raised to the k is going to be the sum of k choose I times x to the k minus I times h to the I. So as the power of x counts down, the power of h counts up, and k choose I ends up with symmetric values as well. As you're not choosing I, you're choosing k minus I. Right, because there's only two things here. This means that here we can replace x plus h to the k with that monstrosity. So typically we don't do it. It's perfectly fine. We're basically going to get the next terms are all going to still remain, but the initial term, x to the k times h to the 0 times k choose 0 is 1. So here we end up with a coefficient of 1 times x to the k. What do you know? We've already got one of them. Right? So this is equal to k choose k choose 1 times x to the n minus, k, again, k minus 1 plus, with a whole bunch of other stuff that have h's in them. And then this is the limit as h goes to 0. So that means that that last bit, which is all the rest of the terms, all have h in them. They get wiped out. Whereas the first term here, this is actually h to the first, and then all of this is divided by h. Right, this is a terrible organization, sorry. But nonetheless, the point being here, our h's on this term will divide out, 1h on the rest of the terms will divide out, but this still has h's on every single term. So that's going to be equal to 0, which means that what we have left at the end of this is going to be k choose 1 x to the k minus 1, which is equal to k times x to the k minus 1. So anytime that we have x to the k, its derivative is going to be k times x to the k minus 1. Now the writers of the GRE book did something else kind of nice, which was that they said that the derivative of u to the k is going to be equal to k times u to the k minus 1 du. Now this is how I start my differential equations class, is that I remind people that what we really care about is this generic derivative operator. It is not with respect to any particular variable. So what it does instead is it says we're just going to take the derivative as the chain rule does of every little bit as we go through everything. So here we know that this is going to be a power rule. We just do this, you know, u to the k derivative is going to be k times u to the k minus 1. Then we have to take the derivative of the inside, du. Now it is very possible that this is still in terms of x or t or whatever. U is still a function. So then you have to determine, like, okay, with respect to what variable, and therefore with respect to what variable did we take the derivative all the way back at the beginning. Things start canceling out. You don't get a little term at the end like du. But I prefer it that way for my differential equation students. Cool. And then I just talk right through ads. So, you know. Good times. No wonder everybody's so impassive. Stoic. Okay, next one. E to the u. Again, we've more or less been doing this just as functions of x, and so therefore we're going to keep it that way. But same deal when we start looking at it in terms of e to the u. Right, this is the limit as h goes to 0 of e to the x plus h minus e to the x all over h. This is going to allow us to split limit h goes to 0 of e to the h times e to the x minus e to the x. Whatever, that's fine. Which is then going to be limit h goes to 0 of e to the x multiplied by e to the h minus 1 all over h. Right, so why do we care about that? Well, as with all the rest of our derivative or limit rules that we were talking about earlier, this is going to end up being 0 over 0, which is an indeterminate form, so we cannot do anything with it in terms of just like plug in 0 for h. Instead, we have to figure out what the limit of this thing is. What is the behavior on either side of h equals 0? So one of the many ways that we could do this is come up with a table of values that get us an approach for what's going to happen. So if we pick h values that are at 0.1, 0.01, 0.0001, 0.000001, and negative 0.000001, negative 0.0001, negative 0.1. Let's start. Right? Let's start with 0.1 and then move toward these smaller and smaller and smaller values. So what we want is, let's get rid of this and then put it in the right place. What is e to the h minus 1 all over h going to be for these values of non-zero h's? So, flashbang out. Okay, what we're going to do is move this down underneath. Y1 is equal to e to the x1 minus 1 over x1. Right? So here, if we do 0.1, right, we get an actual value. Cool. If we do 0.01, we get another value. No, don't do that. 0.0001. 0.234561. Okay, and then we do the same on the negative side. So a negative 0.1, negative 0.01, negative 0.0001, negative 0.23, nope, 6. All right, this 1 notwithstanding, right, because that's not actually 1, it's just 1.0000005. No, it's got to be complementary to this one. Very approximately. Right, it's not off by exactly the same amount, but it's really, really close. So, okay, this is 1, 2, 3, 4, 5, 6, 7 zeros after 1. So 1.0000005. Right. I'm gonna want that. Oh wait. Just take a picture. Obviously. Right, and then we go like this. We get the screenshot. Nope, we get pictures. Screenshot. Scroll all the way to the bottom. 813 at 2308. Yes. That. Right? Those numbers. 1.0517092, and there's more stuff after this, right? These are terminated decimals, but that doesn't mean that that's it. All right, and then again, all of this ends up with 1.1234567 with a 5. Again, I'm not 100% sure that that's the correct value, but I'm pretty sure. Whereas on the negative side, we get 0.1234567 with a 5 after it. 7 nines with a 5 after it. So, where's this trending to? Okay. Even this one knew the answer, right? It was trending to 1. We could see that it's very obviously trending to 1. Does that mean that that is 100% accurate every single time? Well, not necessarily. It could be off by some amount. Now, I do happen to know that in this particular case, that is 100% correct. Okay, so this says that the derivative of e to the x is going to be equal to, this is now e to the x times 1, or just e to the x. So this becomes super important in terms of functions. At one point, there was a time, believe it or not, where what we wanted was a function that was its own derivative and didn't have a particular name for it. Right? That time between Sir Isaac Newton and Gottfried Wilhelm Leibniz and Euler. Leonhard Euler, who was a Swiss mathematician, who was a student of the Bernoulli brothers, Johann and Jakob Bernoulli, who were correspondents with Newton. So it didn't take a huge amount of time, but, you know, still took some time before people realized what it was that we were looking at. Love the accents. Yeah, I try as much as I can to put someone's name in their correct accent, give or take. Now, granted, I only speak Bavarian German in the first place, so, you know, that's like where the accent's going, not Swiss German. They might not like it, but... Germany just can't do it, yeah. I mean, it's fair. I find really it's a matter of finding the correct vowel pronunciations. And then, like, once you figure out the vowel profile, almost everything else falls into place. You know, the weird Asian names. Okay. Yeah, the weird random consonant changes kind of tend to throw me. But I picked up an app to help with learning Icelandic, and let me tell you, when people say it's a hard language, they're not kidding. Just to get the pronunciations isn't too bad, but like to get actual like grammar and stuff like that is wild. But I'm a big fan of, for instance, oh, here we go on another tangent. Oh, yeah. I mean, I know that most of the time you have a consonant coupled with a vowel. And, like, very rarely are they... Wait. What was it? The... vowels are allowed to be alone, but consonants are not, or something like that. In Japanese, yep. But yeah, I'm a big fan in Icelandic of these characters. First of all, it's kind of like math character, you know, the partial derivative when you write the D sort of shape to it. It's exactly the same. And then this right here is pronounced ev. With a voiced th like there. So this is aðborða. Borða. It's also been a long time since I've actually practiced. So, whereas aðþurfa is the voiceless th, as in think. and this is called thorn. Or I guess, as in thorn. Come on, man. So we got off of the plane and went into downtown Reykjavik, and all of the signs are in Icelandic, of course, but this is the first time that I've actually seen Eth and Thorn. I'm like, shit. I don't know what this is. I'm in a place where, everybody speaks English, pretty much, because they're like a tourist industry country. And they're just like, we need to be able to speak English, and just decided that, English was going to be the language they learn. I don't know exactly who decided this or when, and it's probably an easy enough history to look up, but... why not Norwegian that everybody learns or something? But it may have something to do with just, again, the numbers of people from every country that they host. So yeah, when you're learning Icelandic and you have thorn and eth that pop up, very interesting. So then it becomes a matter of, again, you're just learning as much as you can about each individual language and like what's the particular bend that they have on their consonants and vowels. I also had a student who's I've told this before, but and I'm just going to put Professor Zhang's name here because again, my professor's name was Yitang Zhang, or I'll get to it, but or Tom, as he often was called, just among colleagues. He was the guy who, again, solved the first couple of steps in the twin prime conjecture, which has since been knocked down from we have no idea how far apart an infinite number of twin primes can be, to now, well, he knocked that number down to 70 million. Now, I don't know exactly why 70 million. I tried reading his paper. It's really hard for me. Some of you all might be able to get it. But, so Tom's paper, Professor Zhang, his paper said there are now an infinite number of twin primes that are 70 million apart. And people saw it and went, oh. And they were able to start whittling that number down. And they worked on the big project that has like all the math people doing the community mathematics online. They started hammering away at it over and over and over. And they're down to like, I don't remember, it's like 300 or something like that. Twin prime spacing, Zhang. Right, so where are we today? Come on, guys. Come on. Okay, twin prime gap today. upper bound. There we go. Less than 70 million. There we go. Polymath project improved the bound to 246. Assuming that the Elliott-Halberstam conjecture and its generalized form, the bound has now been reduced to 12 and 6, respectively, for two things. Whatever those two things are. Oh, all gaps and minimum size gap. Okay. So the limit on all gaps has theoretically been bound to 12, and the minimum gap size has been theoretically reduced to 6. So that's like really close to 2. It's like the twin prime conjecture might be on the run. I mean, it's already on the run, but it might be cornered like within our lifetimes, and that's pretty exciting. Okay. Anyway. So I'm sticking Professor Zhang's name on the end of this. So yes, I see this name on my roster, and I'm like, And so I go over it in my head like 30 times, and I'm just like, okay, I think I'm gonna get it right. You know, I think that this is how these things are pronounced. And I get to the end of the list, and I go, and she starts to raise her hand because she knows that I'm just struggling with it. And I said, Zhang Zixiang. And her hand freezes. And she goes, and I said, are you okay? And she said, yeah, I just never heard a white boy say my name right. Oh, I'm so sorry. And I'm like, no, you are correct. GG's. And like, at that point, I had listened to, I don't know, probably 30 hours of Pimsleur's Mandarin. So like, I sort of have a feel for it, but I still don't know what it actually looks like. You know, the X as like a Z sound, Q as a ch, and the NG is typically swallowed a little bit. So, So, Zixiang. Pretty close. So, at the very least, I shocked her into thinking that I was 100% correct, when probably I was only about like 70% correct. But, you know. Woo! Anyway. Yeah, good times. So we come over here and we say that we are in fact going to get our man, this computer is so far behind. Yes, I definitely cannot write Mandarin in any form. In any form that anyone other than an American would be like, yeah, okay, I get it. I can only write them in Roman alphabet, but they don't do that. Oh, I told you about Greece. When we went to Chania and then Heraklion, we went into the hotel and, like, you know, I have my phone sitting in my hand like this, and I'm looking at the guy and kind of going like this and trying to, like, pronounce the Greek. And he was just so over the moon enthusiastic that I was trying. We could not communicate one iota. He was just like, yes, yes, good job, good job. I'm like, I mean, no. It is not, in fact, a good job, but I will take the win. Okay. So here, h goes to 0 of, again, e to the x times e to the h minus e to the x, all over h, ends up with the limit as h goes to 0 of e to the x times, and now we get the e to the h minus 1 all over h, which happens, that all goes to 1, so we just get e to the x. Again, e to the u, when we're taking a generic derivative, is then going to be right, e to the u erg. Hang on. Generic. D of e to the u is going to be equal to e to the u times du. Again, the du is going to be our chain rule additive that needs to be placed on the end in order to say, well, it kind of depends on what variable you're taking with respect to here. All right. So what about a? Well, more likely I do b, right, base, to the x. So generically, how do we then work with this? Well, this is going to go through the same process as e, but now we just replace all of the e's with b's. Okay. Right, so this is going to be the limit as h goes to 0 of, again, e to the x times, or no, sorry, b to the x. B to the x multiplied by b to the h minus 1 over h. Now, what is a person to do with all of this? Well, in this particular case, we can say, wait. Yeah, okay. We could say that, again, this is going to all the same stuff. But then we have a little bit of a problem in that we don't actually know what b to the h minus 1 over h is going to be. So unlike e, which just gets us 1, we would need to do all of that process over again with some other b, right? Whatever b happens to be. And for instance, if we do this with just a 2 instead of e, right? All of those numbers just changed. So our approximation is somewhere between 0.69314716 and 0.69314772, which again probably has more stuff after it. It's probably 719 or something like that, or 71. I mean, it only has to be 716. But Could be any of those values up through, in fact, 47249, right? Not likely, but possible. Most likely the last number after this is going to be a 0 because it clipped the number of decimal places it's using. Whatever, it's just rounding. But again, these numbers are now all different. So like, what are we going to do with this? Well, one way we could do it is try to find out what number is close to 0.69314716. Or we could then say, well, we do know what this is if that number is e to the h. So we also have a base conversion formula. So a b to the h is going to be equal to e to the what? Well, in this particular case, there's a few ways we can do it. We can end up saying this is going to end up being e to the natural log of b to the h. And then we don't have to change anything else in the entire setup. Okay, and then natural log of b to the h is going to be e to the h times natural log of b. Right, and then we've got now multiplication in the exponent. So then this is going to end up being, again, e to the h times e to the natural log of b. I think that's going to actually cause us more of a problem. So let's back up a step, and let's keep it here. Right, h times natural log b. Okay, now, we don't have that here. If we just change the top one, then we don't have the same relationship that we did up there with e to the x, or e to the x. No, e to the x. Gotta emphasize the correct syllable. That's really hard for me to do. Okay, so this is going to be limit h goes to 0 of b to the x times. This is now going to be e to the h times natural log b minus 1 over. This can be h, but then the problem is that that number down there in the denominator and that number up there in the exponent don't match each other. So we're going to force this to be the same number, which means that we're going to multiply the denominator by natural log of b, which means that we also need to multiply our numerator by the natural log of b. This now goes to 1. And now we've got that the limit as h approaches 0. Oh, look, there's no more h's anyway, so we can just get rid of all that. This is now going to be b to the x multiplied by the natural log of b. Or I guess in this case, right? We're doing b to the h into e to the h natural log b. So we get b to the x multiplied by natural log b. Okay. So then, with any other function, we're doing the same stuff, really. This is going to end up being the... Okay. Right, what about the natural log of x? Well, if y is equal to the natural log of x, then we can convert that back and forth into e to the y is equal to x. And now we can just avoid the problem altogether by using what we call implicit differentiation. Right, by taking the derivative of e to the y and also taking the derivative of x, right, again, y is equal to natural log of x is what we need to hold on to as we make this little thread here. Derivative of e to the y, we already know that, right? It is e to the y times dy. And the derivative of x is dx. Again, these are generic derivative operators, all that good stuff. Then, if we want to get dy dx, then we need to shift things around a bit. This is now going to be 1 over e to the y. Well, y was the natural log of x. So now we have e to the natural log of x, which is just 1 over x. So our derivative of y is going to be equal to dx over x. And likewise, if this is a function not of x, but of another function u, then we get du over u. Same deal. Right, so this is implicit e to the y, or derivative e to the y is equal to dx, and then go from there. So this is 1 over x. I seem to be slipping on something. Okay. 20 more minutes until ads run. It's pretty close to midnight when they do. Okay. And then generically, again, what about the log with base b of x? And then this is going to just be run the exact same way as we did before. So this is going to be the derivative of b to the y is equal to dx. And we get the same thing, guys. It's the exact same thing. The only difference is that now we have to worry about the location of that log of b that we had from before, or natural log of b. So if we do b to the y is equal to x, and again, take the derivatives. Right, b to the y, natural log of b times dy is equal to dx, shift again, dy dx is equal to, this is now going to be 1 over b to the y times the natural log of b, and b to the y, again, was just x from up there. Right? We don't even need to plug it in because we have the other equation. In fact, right? Because we could have just said, hey, look at this. Oh, no, wait. Hey, look at this. It's the same thing. And then we could have just replaced it directly with x in the denominator. Thank you for the follow. Welcome on in. My name is Obi-Wan Pez. This is N Simplex Pachinko. We are doing some GRE work. So anybody who's getting prepped for their graduate record exam, feel free to ask any questions. Anybody who just wants to know stuff about mathematics, also feel free to ask any other questions if you want to get to know who I am, all that good stuff. So feel free to ask. I'll take regular talk breaks and just talk about all sorts of other stuff if there's somebody who prompts me. Zach will attest to that. We just got off on a half-hour-long conversation. All right, so this is going to be 1 over x times the natural log of b. All right, works out pretty easily. And at this point, there's also a lot of hey, we know the derivative of this thing. We don't need to go all the way back to the definition of derivative. We can actually just use some of the other stuff we found and rework it. So, like we did for implicit differentiation, if we know what the derivative of e to a function is, which again is e to that function times the derivative of that function, then we're able to figure out, again, e to the y is equal to x, derives to e to the y dy is equal to dx, and we want dy dx as our dependent variable, I guess is a good way to put it, to be one of the sides of the equation, and then we just get 1 over x there. Okay, that sort of stuff. So something new, as in like trig functions, are unfortunately not going to be quite as easy. Sorry. Problems with facial hair. So we say that if we take the sine at some particular x value, again, we want to take the derivative of this thing. Then our initial principles tell us that we should take the limit as h goes to 0 of sine of x plus h minus the sine of x all over h. All right, so the sine function, sum of angles, is going to be the sine of x times the cosine of h, not hyperbolic cosine, plus the cosine of x times the sine of h. Move over a little bit. Minus the original sine of x all over h. Okay, so there's a few different ways to work at this. One is that we're going to separate these out into stuff we can factor and things we can't. So, for instance, the sine of x times cosine of h minus sine of x is something that we can factor a sine of x out of. And then what we're left with is the cosine of h minus 1 over h. We'll come back to that in a minute. Okay, plus the limit as h goes to 0 of the cosine of x times sine of h over h. Again, our cosine of x here has nothing to do with h, so limit as h goes to 0 just doesn't affect it, right? We could, in fact, swap the locations of those two things, and it will not matter one bit. Okay, so there's a couple of ways to address each of the parts. One, this thing right here. There is the law of small angles, right? Which is a more like vibes approach to math, but it works. We do know that as h goes to 0, that sine of h is going to be approximately h. Right, again, that is like a vibes statement. It has been proven, but we have not proven it ourselves. You can do it a few different ways. So, like, you try to figure out what the 0 is for sine of h minus h. You can try to do some other, I don't know, you could do a lot of stuff, but I mean, finding the 0 is just h equals 0. But you can look at other numbers and say, like, the sine of 0.0001 is approximately what value? And again, it's 0.0001, or very, very close to it. Okay, there is the possibility of doing the same thing we did earlier. We could come up with a graph to show that sine of h over h is very approximately 1 as h starts getting closer and closer to 0. Again, you can't let it be 0 in a graph or on your table. Right? Can't let it be actually 0 in a graph or a table, but you can get it pretty close and say, like, okay, what is it doing? What's our trend doing as we get closer and closer? So one of the ways we could do it is we change this thing right here, 2 to the x minus, or x sub 1. We can change to let this be instead sine of x sub 1. But this 1 that's next to it isn't there. So that 1 minus 1 that's here needs to be deleted, because in what we're doing, the value it's approaching is 0. Right? So now as we get even close to 0.0001, there are so many 9s in this, you know, 0.9999999, whatever, that it's just going to be like, yeah, it's close enough. Don't worry about it. And we're going to end up getting 1, or essentially 1. Right. This one here. 1, 2, 3, 4, 5, 6, 7, 8 9s and an 8. So that's what we get. Okay, Then we want to do the same with cosine, but then we're going to flip that back to a minus 1. Because in this case, right, cosine of h minus 1 over h. Our cosine of h, if h were allowed to be 0, it would be 1. So 1 minus 1 gets us 0, divided by h is going to 0. That's 0. So indeterminate form as is, cosine of, or well, 0 over 0 is our indeterminate form. So we can't allow that to happen, so we just pick numbers that are really close to h being 0. Our cosine of h becomes really close to 1, and then we get a number that's, the cosine of h minus 1 over h, which then gives us these values. So we're pretty close to negative 5 100ths, and then negative 5 1,000ths, and then negative 5 100,000ths, I think. It might be actually negative 5 1,000,000ths. Anyway, and then it keeps going. So as we add more zeros, we just get closer and closer and closer to 0 itself. And that makes sense if you think about a cosine function, right? This flattens off. So on top, it would have a slope value of 0. So this is going to be a sine of x times 0 plus cosine of x times 1. And so that means that we're going to get the derivative of sine of x equal to the cosine of x. All right, adds are going to start, so I'm going to start that. Probably get up and stretch at least. Get more water, I suppose. And we will be back in 3 minutes. So thank you so much, everybody, for coming. And yeah, we'll be back in 3. Get up, stretch. Get yourself a snack, meal, water, whatever you need. And we'll be back in just a bit. Thanks so much for coming. Thank you everybody for sticking around. We're going to do some small things here. We'll redeem AR, which is in tribute to John Gould and the Down East Maine dialect. So we're going to do a vocabulary word or two out of John Gould's Maine lingo, a wicked good guide to Yankee vernacular. Alright, we're going to pick a sort of flippy random page here. Okay. Ice cream shot. Ice cream shot is an easy hunting shot. In the days when ice cream was brought to sporting camps in large wooden tubs packed with ice and salt, the tubs were returned to town for credit. The chore boy would dump the salt brine from them in a certain place behind camp to attract deer, whose delight in finding salt is well known. Then, in hunting season, a sport who had not shot his deer but had come to the end of his outing would be given an ice cream shot on his last day. No need for paying guests to go home empty-handed. Saltin', or baitin' game, was and is illegal, but the ice cream water had to be dumped somewhere, and the term is used to describe an easy shot, as when a buck stands side about 20 yards away, whether salted or not. It is also applied to easy scores in athletics, such as an unguarded basket or a football play that lets a backfield man score standing up. Ice cream shot. That was a nice long one. Alright. Went downstairs, got some cherries. Last of them in this batch. Gonna have to go buy some tomorrow. We've got a couple of fruit bats in the house. Our kids just constantly eat fruit over and over, which is great. I love it and all that. But I just wish that they would take reasonable portions. And second little thing that we got downstairs was a little tiny bottle of whiskey that was brought over by our friends who have since departed Yorkshire back for America. So this one is flavored as Yorkshire pudding. For anybody who is not familiar with Yorkshire pudding, okay. Generally speaking, Yorkshire pudding is like unsweetened fried dough that you would then put some sort of like meat mixture into. It's savory, generally speaking. So savory is not generally something you would associate with whiskey. However, this is actually somewhat sweet smelling, so it's kind of interesting. I don't see it. It's okay. It is from the Yorkshire Pudding Beer Brewery. Apparently they have a distillery as well. Malton Brewery. Oh, from the company that brought you the iconic Yorkshire Pudding beer, we're proud to have developed a blend of whiskeys aged in traditional oak barrels. We have created a sophisticated balance of Yorkshire puddings in a traditional whiskey. So they apparently, or our friends must have gone to some sort of event where they were giving these away or selling them for, you know, cheap. Like I said, it's okay. There's probably a reason why it was sitting on their cupboard when they left. That's interesting. Does it have a date? No, not really. It would have been interesting to have like a bottled or purchased date on it. But generally speaking, whiskeys will not need that. Nothing can live in it. Okay. So we have done some of our we have done some of our derivatives and gotten at least a couple of tables going where we found the derivatives of these particular functions. And then also we would like to get the other trig functions. So ddx of cosine of x is going to be equal to, here again we go with the cosine of x plus h minus the cosine of x all over h, and that is limited as h goes to 0. Limit as h goes to 0 of cosine of x times cosine of h. This one, however, is minus, sine. Sine of x times the sine of h minus cosine of x all over h equals, take the limit as h goes to 0 of, take the cosine of x out, and left behind is cosine of h minus 1 all over h minus the sine of x times limit h goes to 0 of sine of h over h. Hey, we've played this game before. The limit is h goes to 0 of cosine of h minus 1 over h is 0, so this is cosine of x times 0 minus sine of x times 1. So this is going to be the negative sine of x equal to the derivative of cosine of x. Alright, so what about the rest of the trig functions? So we got tangent, cotangent, secant, and cosecant. Alright, this is all just going to be the same stuff. Actually, no, that's a lie. Now that we've got the derivatives of sine and cosine, now all we have to do is say, okay, this is going to be the derivative of sine of x over cosine of x. Cotangent is going to be the derivative of cosine of x over sine of x. Secant is going to be the derivative of 1 over cosine of x. And cosecant is going to be the derivative of 1 over sine of x. So we can do this stuff as either product or quotient rules, and then clear out all the rest of them. So it's not terribly difficult to figure this out. Just kind of time consuming. Alright, ddx of tangent is ddx of sine of x over cosine of x. And again, you could decide how exactly you want to do this. Product rule is, or quotient rule is easy enough. Product rule does require you to keep track of negative exponents, and you know, some people don't like it, or it just gets a little complicated. So you know, you can decide what you want to do with that. So quotient rule on this, it's going to be the derivative of sine, which is cosine, times the denominator, which is cosine, minus the the numerator, sine of x, times the derivative of the denominator, which is a negative sine of x, all over the denominator squared. So cosine squared x, which is going to be cosine squared of x minus, multiplied by a negative, is going to get us a plus sine squared x all over cosine squared x. The numerator is equal to 1. 1 over cosine squared x, which is, right, dx of tangent of x is going to be equal to the secant squared of x. So our tangent is going to get us a secant squared when we take its derivative. All right, what about cotangent? We're just kind of doing this the opposite direction, right? The ddx of cotangent of x is going to be equal to derivative of cosine of x over sine of x. It's going to be equal to, again, it's a quotient rule. The denominator is going to be sine of x squared, sine of x squared, sine squared of x, whatever you want. The first term is going to be the derivative of the first term is a negative sine x times the denominator is also a sine of x. The next is going to be negative. Numerator is cosine of x. And then we're multiplying by the derivative of the denominator, which is also cosine of x, which is a negative sine squared x minus cosine squared x all over sine squared x. The numerator becomes a negative 1 because if you remove the negative from both of those terms, then it becomes sine squared of x plus cosine squared of x, which is 1. Just there's a negative now. So this is going to be a negative 1 over sine squared of x, which is going to be a negative cosecant of x. So d dx of cotangent of x. Right. And what if we start with secant? Well, that's d dx of 1 over cosine of x, which is going to be equal to, denominator is going to be cosine squared x. Numerator is going to be the first term, your numerator, derivative. We know that the derivative of 1 is just going to be 0 times the cosine of x minus 1 times the derivative of the denominator is going to be a negative sine of x. Okay, so this is going to end up being 0 plus sine of x over cosine squared x. There are a few ways to deal with this. So yes, we could let this be the sine of x times secant squared of x, but I have never seen it said this way, ever. Most people probably would not like it. So instead what we want to do is look at this as, hey, if we take a sine and a cosine and do their own thing, then we also have one term left over for the other thing. So now we have two terms, two different functions, but they both have a 1 as an exponent. Quite frankly, I like that a little bit better. It's a little cleaner. Sine over cosine is a tangent, and then 1 over cosine is a secant. More commonly, it's reversed, so that the derivative of a secant is a secant tangent. Like to use the particular function's name in its derivative first, if that's the case. Most of the time. All right, d dx of, what about cosecant of x, which again is going to be the derivative of 1 over sine of x. Again, denominator is going to be the sine squared of x. And let's see. Okay. First term is going to be numerator derivative is 0 times the denominator, sine of x, minus numerator 1 times the derivative of the denominator is cosine of x. And again, we run into the same deal as we did before. This is now going to be a negative. Let's do cosine x over sine of x. And then left over, we have a 1 over sine of x. Or we now have a 1 over sine of x is cosecant, man, times a negative, we'll stick the negative out front, a negative cosine over sine is a negative cotangent. So the derivative of a cosecant of x is going to be a negative cosecant cotangent, which is very similar to the secant tangent that we got for the derivative of the secant up above. And let's see. Actually, we did all of them, didn't we? Yep. Okay. Tangent, cotangent, secant, cosecant. We're good. So that's all of our trig functions, or at least the basic ones. And then they also go with, what about all of the arc functions? So they've actually only discussed what about arcsine and arctangent. The rest of them are going to be basically do the same thing over again, so that'll be left to as an exercise for the viewer. So if you want to determine what the derivatives for arc cosine, arc secant, arc cosecant, and arc cotangent are going to be, you can go off and do those on your own. But essentially, what we've got here is that, well, y is equal to arc sine of x, right? So we could just say that sine of y is equal to x and do implicit differentiation just like we did on some of the log stuff from earlier. So now we take the derivative of both sides and we get that this is a cosine of y dy is equal to dx, and again move that stuff around a bit. Dy dx is going to be equal to 1 over cosine of y. Okay, well, how do we figure out what the cosine of y is if we already know what the arc sine of if we already know what the arc sine is? There we go. So just in terms of how this all works, y is going to be the angle. It's the input of the cosine. It's the input of the sine. It is the output of the arc sine. So it is an angle. Then we know that this is a ratio. So the inside portion, arc sine of x, is actually a ratio x over 1, which is the sine ratio for y. So it's the opposite. It's going to be x over there, and 1, which is the hypotenuse. It's not there, but it is there if you think about it, right? Because it's over what? You know, it's opposite over hypotenuse. So make it into a fraction. Give those parts over here. So our third side, our adjacent side down here, has to then be the result of a Pythagorean theorem where we took, like, it squared plus x squared is going to get us 1 squared. Or if we rearrange stuff, let's just call this a down here, right? A squared plus x squared equals 1 squared. So a is going to be equal to, we know that's going to be 1 squared minus x squared, but then we need to take the square root of all of it. Right, so then here, 1 minus x squared. So the cosine is going to be the adjacent over the hypotenuse. So this is going to end up being 1 over square root of 1 minus x squared, and then all of that's going to be over 1. So that doesn't matter. We don't have to do anything to get rid of our compound fraction. We don't have a compound fraction. Right, so this is going to be our arc sine here. And then we want the arc tangent derivative, which again is arctangent of x over 1. Which again means that y is our angle, and then the tangent is opposite over adjacent, so that's x here and 1 here. So then what is the hypotenuse? Well, 1 squared plus x squared is equal to h squared, hypotenuse squared. So then we have to take the square root of all of it in order to make sure we just get h, hypotenuse, whatever you want. So this says that now we're going to get the tangent of y is equal to x, and again take the derivative of both. So once we take the derivative of this stuff and the derivative of that, we end up with a dx here and a secant squared y dy over here. This is going to end up being dy over dx is equal to 1 over secant squared y, which is equal to just the cosine squared of y. That's it. Well, we know what the cosine is here. Again, this is adjacent over hypotenuse. So dy dx is equal to 1 over square root 1 plus x squared parentheses squared. So dy dx is equal to 1 over 1 plus x squared. Man. Awesome. Just real quick, as a note to anybody who's new here, e to the 2i pi, also in chat right there, is Zach. He has also been doing math. He's one of our math streamer friends, among other people here on Twitch. We also have multiple other people who are here tonight. So we got Academy of Useless Ideas, also known as Slim. Thanks for coming on in, bring your community. We've also got Rogan27 is not a member of our group, but is an archivist with Virginia Tech, and goes and finds like really cool stuff that's in the Virginia Tech archives, and then does streams on it every Wednesday. Rogan also does game streams, usually on Monday. Although, right, multiple days. Monday is typically a one-shot night, although one-shot has a very loose definition. Let's see, Dawn Factorial, who is currently? No. Last streamed Sifu, and has been working really hard at not aging his character up. But it is a hard game. We also have Dr. Gold at Actual Education, who does often math stuff, can also be doing other random things on random nights, but typically leaves the channel for mathy type stuff most days. So those are some of our awesome streamer friends who do all sorts of cool stuff. And they're around, often enough. We're all sort of friends, pass communities around to each other, and meet new awesome people. So hopefully you will also meet some awesome people out of that group. Okay. So let's go back to our table. Yes. Right here. This is going to be the arc sine and the arc tangent. Nope. Implicit differentiation. D of sine of y is equal to d of x. D of tangent of y is equal to d of x. Okay. And again, what we got here I didn't leave enough room. That's fine. It's all fine. Just get rid of that one. Yep. So anybody who doesn't know me, my name's Obi-Wan Pez. This is N-Simplex Pachinko. We do mathy type stuff on Mondays and Wednesdays. Currently doing math education on Monday and general math knowledge. Currently working on the GRE stuff, which means that we just have like a source of student problems and things like that to work on, and a sort of loose curriculum guide to follow. At some point, we are going to start up a class for either differential equations or pre-calculus or calculus. So if anybody's interested in that sort of stuff, we use a Discord server. I don't have it up. Cool. Oh. That belongs to one of our other streamer friends, Penn Center, who currently has been doing all sorts of gamey type stuff while he's getting used to his new role as a department chair at a British Columbia University? 2-year? I forget. I myself worked at a community college in Maryland in the United States for about 15 years, and then my family decided to up stakes and moved to Yorkshire for 3 years in the UK. Quite different. Quite lovely, as they might say here. My kids absolutely hate it when I do that. Tangent was a secant tangent. No, secant squared. It's alright. We're okay. Cotangent was negative cosecant squared. Secant was a secant tangent. Cosecant is a negative cosecant cotangent. Arc sine was 1 over square root 1 minus x squared. And arctangent is 1 over 1 plus x squared. Again, the other four, the arc-cosine, arc-cotangent, arc-secant, and arc-cosecant, are not difficult. And if you know your calculus and your algebra well enough to manipulate this stuff, it's super easy. So it's following a similar-ish template to what we were doing here. Right, so first off, switch it back to just a sine statement, but it's going to be a function of y rather than a function of x, and then work from there. Go down. Here we go. Pen Center's Discord, the elements. For anyone who is interested. Again, we typically do mathy kind of things, and of course, like any Discord server, there's also all sorts of other stuff going on. But we are going to try to get classes that are run either through this Discord or one of the other Discords from our other math teachers. So, like I said, I do pre-calculus, calculus, Calc 1, 2, and 3, and differential equations. Those are kind of like my specialties, and I would be comfortable enough teaching, well, Calc 1 and 2 I've taught before. Calc 3 would be a stretch. It's not humongously difficult, but I don't have an actual curriculum with all of my slides and things like that. All right. 1 minus x squared? Yes. Okay, good. Okay. So that comes to the end of the lecture part of this. And now come the example problems. So here, find the following derivatives. So a, f of x is equal to x to the third e to the negative x squared. No, to the third. It doesn't really matter because they're not actually going to affect each other, but nonetheless. Minus x minus 3. Okay, then we'll do b over there. G of x equals. So if we want to find the following derivatives, right, f prime at x is going to be equal to this. First and foremost, looking at the large-scale structures of everything, we have addition, subtraction between these two terms, or the three major terms. So with addition, subtraction, we do not have to pay any special attention to the rules in terms of, like, you know, product rule is very different than a sum rule. So all that's going to happen is that the coefficient, a -1 and a -3 in front of x and 1, technically, respectively, those coefficients are just going to get kicked out front. Nothing's going to change. And then we have the derivatives of each of them. So this is technically x to the first power, and we know what a power rule does. So we're going to take our current power, it's going to drop out front as a multiplier, it gets ticked down 1, and then, well, that's it. We take the derivative of what's inside of that, which at the moment is nothing. So here we end up with a -1. Derivative of x is just 1. It's 1 x to the 0. Okay, and then here we get a -3 technically, right, times a 0 because this is just a constant. Okay, The other thing that we have to worry about is what is the structure of this? Well, we've got an exponential function in it. That's not a big deal. We know where those were. But the bigger structure, the largest structure that involves the most things, is multiplication. So this is a product rule. We're going to need to say, let's take the derivative of x to the third. Right, we're going to be slightly rude about this. We're going to take the derivative of x to the third times the second part, e to the negative x to the third. Nothing happens. Then the product rule says we're going to continue by saying this is going to add to the first part, x to the third, doesn't change, times the derivative of the second part, e to the negative x cubed. Derivative. Right, that's what our product rule is going to do. Okay, so then what do we do with that? F prime is equal to. We do the product rule. No, we're doing the product rule. We do the power rule on x to the third. So here, this is going to cause the 3 to come down as a multiplier. Our exponent ticks down from 3 to 2. Then we multiply by e to the negative x cubed. Nothing changes there. Plus x to the cube, or x to the third. Nothing changes there. Times the derivative of this function. So e to the u, right? E to the negative x to the third is going to be e to the u, which means that when we want the derivative with respect to x of e to the negative x cubed, this is going to translate as us taking the derivative of e to the u, and the derivative of e to the u is equal to e to the u times du. So the derivative of that u stuff. Okay, so now this is going to be just the same exact thing, e to the negative x cubed, but then we multiply by the derivative of negative x cubed. So we can do this staged and say, okay, let's hold on to that for a minute. Right? Prime, meaning take the derivative of the thing in the parentheses. So take the derivative of negative x cubed. Okay, minus 1, because here we had a 1, negative 1 times 1, and then a 0. So that doesn't affect the rest of this. Which then means f prime of x is equal to, this is going to still be 3x squared e to the negative x cubed, plus x cubed e to the negative x cubed times, what is the derivative of negative x cubed? Well, the 3 comes down as a multiplier and becomes negative 3 times x to the 3 ticks down to become 2 again, and then minus 1. F prime is equal to 3x squared e to the negative x cubed. All right, and then here we've got a minus 3 when we multiply all this stuff to the front. Negative 3 times x to the 3 and 2 makes 5 times e to the negative x cubed minus 1. And no like terms to collect. We could, in theory, factor out the e to the negative x cubed, but I don't think that that's going to do us really much good. We can do it just to be like, well, you know, this is a polynomial. So we can have this polynomial bit stuck out here. I'm not going to do that, right? You could be picky about it. You can decide that you do or don't like it. Kind of up to you. Okay, g of x is equal to, this says log of sine of x, sine squared of x divided by cosine of x. So g prime is going to be equal to, we could do this as a product rule where cosine of x has a -1 as an exponent. You do have to be careful. It is not the inverse cosine. So be careful where you put that -1 if that's what you're going to do. Or we do it as a quotient rule. Again, let's stage this. So we take this as log of sine squared of x prime times cosine of x minus log of sine squared of x times cosine of x bracket prime over cosine squared x. Alright, about 10 more minutes till adds. We'll get C done and then probably leave the next one for review probably, or next time. Start next time. G prime of x is. Okay, so with the first one, we're going to use a chain rule here because we have a function of another function. So taking the sorry, the log, just written as log, is many times written as log base 10 of something, or it's going to be the natural log of something. So this becomes a little bit of a sticking point for some people. In this particular case, they explained at the beginning of the book that they're not using common log, they're using natural log as just when you write log. It is kind of a holdover from the fact that we have a base 10 system. The fact that you would use just log to be log base 10, but we're slowly moving in the direction that log should just be natural log, which is also the log base E. Alright, so the derivative of our log, or natural log, was 1 over the function that was on the inside. So sine squared of x. Multiplied by the derivative of the function on the inside, which is going to end up being, well, let's stage it again. So sine squared of x prime times cosine of x was always there, minus again log of sine squared of x times the derivative of cosine of x is negative sine of x. All divided by cosine squared x. Which is now equal to, okay, we've got 1 over sine squared of x times the derivative of sine squared of x is going to be, this is a power rule, so take the 2 down. It's going to be 2 sine of x times the derivative of the inside of that function, which is the sine of x. So the derivative again of the sine of x is going to be the cosine of x, times the cosine of x that was already there. Right? This is the derivative of that thing. And then we just had a cosine come down as well. It was always there. And then this one is going to be negative times negative is a positive. Log of sine squared of x times sine of x. All over cosine squared x. Alright, there's no nice universal way to make this work. So, we're going to... I prefer this to get rid of the compound fraction first. So multiply both top and bottom by sine squared x. Then we just end up with 2 sine of x cosine squared of x. Right? The sine squared of x gets rid of the fraction, the first term, plus sine cubed of x times natural log, whatever you want to call it, sine squared of x. All over sine squared x cosine squared x. Oops. Right, so in actuality, we probably only needed to multiply by sine of x, both top and bottom. Let's change that to 2, and let's change the spacing. Okay. So that's what we've got there for G prime. Alrighty. Well, again, we'll leave it here for tonight. We'll come back next time with that last problem on, well, we'll get arctan, sorry, find the derivative of the arctan of the square root of x, and then also what's the equation of the normal line through the origin to a given curve. So that involves finding the slope of the curve at all possible points, and then figuring out what straight line that is a tangent to this curve is also going to go through the origin. And then we'll also do linear approximations finally, after putting it on here for 2 weeks and not actually doing it. We're actually going to do it next week. So thank you everybody for coming, and we will be back on Friday certainly for Against the Storm. We'll be back on Sunday for Satisfactory Sunday, and then we'll also be back on next Monday and Wednesday for more mathy type stuff. So let's go and see. Let's go and see Rhagodactylus, who is currently looking at Antonio Damasio's We Are Feeling Machines That Think. Earlier, Reiko was working on some... oh, shoot. I just broke it. Was working on some philosophical type questions. So we'll see how it goes just now. So thank you everybody for coming. My name's Obi-Wan Pez. This is N Simplex Pachinko. See you next time.